So it's my pleasure to introduce the next speaker, Professor Sanjeev Arora. He is currently Professor of Computer Science at Princeton University. Professor Arora is best known for his work on probabilistically checkable proofs, in particular the PCP theorem, which is one of the most important achievements of complexity theory in the last 25 years. Amongst his many awards, he was awarded twice the Gödel Prize. First in 2001 for his work on the PCP theorem, and again in 2010 for his work on the Euclidean traveling salesman problem. He was also awarded the Fulkerson Prize in 2012 for his work on approximation ratio for graph separators. Together with Boaz Barak, he is also well known for being the author of a wonderful book on computational complexity, which I warmly recommend to all of you. So Professor Arora will talk about the mathematics of machine learning and deep learning. So.
Good morning. It's my great honor and pleasure today to talk to you about machine learning, which has been my interest for the last 7-8 years. Now, machine learning is, of course, in the news and commercially very important in today's tech boom. What I'll try to convince you today that it's also a new kind of science and an important science. Machine learning has already resulted in machines that look at images better than us, can play the game of Go better than us, can spot certain kinds of cancer tumors in X-rays better than humans, and on tasks like driving cars or translating text between languages, they are approaching human-level performance. So we've all heard about these technological achievements. What is the science under it? The science is of creating machines or programs that improve from interaction and experience. Notice that, unlike the term artificial intelligence, here, imitating human intelligence is not an explicit goal. I see that the slides are cut off a little bit on the right. Hopefully, it'll be OK. So machine learning forces us to confront questions that people didn't quite confront in the last several thousand years, trying to understand what is learning? What does it mean to understand the world? For example, if the self-driving car is on your road, does it know how to solve the following task? What sequence of pixels, because its eyes are cameras, what sequence of pixels correspond to a scene with a pedestrian? Now, these are really simple, even naive questions, because, of course, what does it mean to understand a scene? You never had to explain to anybody. And it's kind of like Newton sitting under his tree and asking, why does the apple fall down from the tree? For thousands of years, people said that's what things do. They fall down. And so it's almost so naive that people didn't even ask the question for thousands of years. And these questions are kind of like that. The difference, of course, from Newton's laws is that there's no simple law which will describe these things. So here's an overview of the rest of the talk. It is in 4 parts. In the first part, I'll give you, at a very elementary level, a mathematical formulation of machine learning. I'll strip it of all jargon that you may have seen and make it very simple, and try to make it very simple and intuitive. Part 2, I'll give you some examples of machine learning, this paradigm that I'll introduce, in action, in more complicated tasks, like unsupervised or sequential decision-making and playing Go. Part 3, I'll start talking a little bit about my work recently and work of other people, where we're trying to develop a mathematical understanding of deep learning. which is the sub-area of machine learning that is having all this impact lately. In part 4, I'll take stock of whatever we've learned and some concluding thoughts. Now, I should say upfront that it's going to be fairly non-technical, almost no math. What my hope is that by presenting it in the simplest possible way, this hall of amazing intelligence and technical depth, the people here will get interested in it and maybe come up with new insights, and I would love to hear those insights. And furthermore, this talk is a tour with many stops, and so it's OK if you don't completely follow one slide. Probably in the next slide, you'll catch up again. So part 1, mathematical formulation of machine learning. Now, operationally speaking, machine learning today, the vast majority of papers written in it boil down to learning patterns from data. I must say that machine learning has been around for several decades, and it did take other turns along the way, and I won't go into that history, but today this is a dominant paradigm. Now, you've all heard the phrase learning patterns from data. What exactly does that mean? It actually is something very simple that mathematicians have known for a couple of centuries. The idea of fitting a curve to experimental data, empirical data. So here's an example of a curve which gives the data points of inflation and unemployment in Japan during a certain period. So these dots, quarterly figures. Now you squint at the scatter plot and you say, well, that looks roughly like a line. And indeed, that line is called in economics the Phillips curve. Here's another example. Gas laws, something we also learned in high school. So it connects pressure, volume, and temperature of gas so that if you know 2 of them, you can predict the third. This was also discovered by fitting a surface to these 3 quantities empirically. Of course, later, statistical physics, in one of its triumphs, explained the gas law from molecular motion. But initially, it came from curve fitting. Machine learning also uses this kind of surface fitting, but with many more variables. Not 2, not 3, but millions or tens or hundreds of millions. And when you fit those curves, you learn complicated patterns in data, just as these patterns were. And that's how it gets the ability to act upon information from the world. OK, so I'll start with a very simple example. This is like the first day of undergraduate machine, or maybe the first week of undergraduate machine learning. Very simple example. And the example is learning to give a numerical score to a rating of a movie on Amazon. OK, so this is the movie La La Land, and here are 2 reviews that I found on Amazon. The first one says, slow-moving, could not get into this movie despite all the awards it has won. And the numerical rating is minus 1.5. And the second is, wow, did not know what to expect and was delighted and loved the homage paid to the musicals of old. And that is a score of 2.5. So the task is the following. You're given a data set of these reviews and their rating score. And the rating score was assigned by a human. And it's scaled to -3 to +3. So you can train your model or your program on this data set of reviews and ratings. And the task is, now you'll be given a new review, just a text, language. And you have to predict the rating score. So now, in line with the discussion we had so far, gas laws and so on, what is the law of movie review scores? Well, clearly the law, if it exists, is going to be very, very complicated. It's not going to be like Newton's laws or gas laws. And so in machine learning, you're happy with approximate laws. And it embraces this approximation because the things it's studying are too complicated. And so let's start with the simplest law we could hypothesize, which is a very simple linear model, which goes as follows. So let's say there are 100,000 words in the English dictionary. That's the number of common words. And the hypothesized law is that we humans, when we rate the movie review, have in our heads a simple sentiment score, a scalar, for each word. So for all 100,000 words, we have a scalar in our head, which is a sentiment of that word. And the review score, well, the review has a bunch of words, is just a total sentiment score of all words in it. The simplest linear model you would imagine. You could consider complications of this, but let's stick with this. All right, so if you hypothesize this law, now if you try to find sentiment scores, if you want to recover these sentiment scores, the parameters in the law, then you're going to solve a surface fitting problem with 100,000 variables. By the way, if the technical staff can see that it's cutting off some part of the slide, if you can adjust it, maybe that'll be great. Okay, so that's a hypothesized law. And so how do you find these parameters, these sentiment scores for words that supposedly we humans have in our head? So call that a variable, theta sub w, for each word w. So 100,000 variables. And for any review, the predicted score is the sum of the sentiment scores of the words in it, so a sum of theta w. And there's a given score. And to try to fit the theta w's, you just minimize the sum of squares of differences between the two. So that's called a loss function in machine learning. And how do you optimize this? Well, it's the classic Gaussian least square fit, which is solvable in a few seconds on your laptop. Okay, and technically it's fitting a hyperplane. It's a linear function, it's a hyperplane in 100,000 dimensional space. Okay, so we saw least square fit in high school science, and this is being done at a large scale. That's it. Okay, so just to illustrate the technique a little bit more, I asked my student to fit this model to movie reviews, and he gave me these scores that he came up with for the various words. So there's a table of scores that you learn, that this fitting learns. And now if you look at this review, love the homage paid to the musicals of old, story was good as well. Well, what is a predicted score for this review? Well, you read out the sentiment scores for the words, for each of these words, and that's these, and you add them up and you get 2.7. So that's the predicted score. So now you look at these numbers, and it's actually interesting to do that in these simple models, and you see good has a score of 0.6. Loved has a score of 1.1. So you realize that this model, which fitted to data, has basically discovered the following patterns, how these words correlate with positive score. So in positive reviews, loved or good appear a lot. So this shows you this idea that curve fitting is finding patterns in data. So now I'm ready to define machine learning a little bit more formally. Machine learning, basically, I mean, there's some exceptions. It basically is a problem of finding a suitable function, mapping inputs to outputs, given examples of this input-output behavior. Okay, so there's a model, and it has some parameters, theta. So theta is a vector of parameters. And these are trainable. You can think of them as tunable knobs. And we're trying to fit this function, parametric function, to the given examples of input-output behavior. So the input-output behavior is you're given an input x and an output y that it produces, and you're given many examples of this, and from that you're trying to learn this function, tune the knobs. So just to relate it to the previous example, there we were learning a model where we were given review text, which you can think of as a vector indicating which words are in the review, and the output is the score, the desired score. Now, of course, the linear model had the property that it had these parameters, theta sub w for each word, and the output of the model on the review is the sum of the theta w's for the words in the review. So now, of course, the prediction of the model and the score may not be the same, and we minimize the sum squared of differences to train the model. So that was for linear models, but you could do it for any parametric family, right? So that's what you have to do. And so for this other model family, the output is f sub theta of x. It could be a very complicated function of theta and x. And the desired output is y. So you have to now fit it. And the training data is a bunch of pairs x and y. And the loss is going to be the L2 loss again, okay, the sum square of differences. Completely analogous. And that's it. So we went from the linear model to the fully general case. It's not fully general in the sense that people use other loss functions, not the squared differences, but we'll ignore that for now. Okay, so that's it. So there's no mystery in machine learning. That's all it's doing. And the formal framework. Okay, so let me be a little bit more precise. So you trained in the previous slide on the data, but of course, what you want the model to do is predict well on new instances. And how is that argued? And the formal framework is inherited from classical statistics, which is as follows. That we are assuming that these samples, xi and yi, are drawn from a probability distribution, namely the distribution on pairs, movie review, and rating score. I apologize for the way the slides look. I think this is a problem of going from Mac to Windows, I think. So the probability distribution is kind of specifying the domain. In this case, movie review and rating scores. And we are only going to train the model to solve this task. It can't grade philosophy homework. So, and we train the model by defining a loss function and minimizing that. And we'll talk more about the optimization later on. And then testing the model involves taking new x's, which the model was not trained on, and seeing how well the trained model predicts its missing label y. So in our previous example, given the review, predict the rating score. Now, this may look mysterious. Wait, what is this missing score, and how do you get it? Well, in practice, it's very simple. You have training data, xi, yi, and you just train on 80% of the data, and then test on the remaining 20%. So that's the held out 20%. And so whatever the model does on the full distribution, you'll see a very good estimate of that on the 20% held out data. Okay, so you at the end test on the remaining 20% and evaluate the loss on the 20%. And if that loss is bad, then either your modeling was incorrect, like the linear model was maybe too simplistic, or your optimization failed in some way. So that's it. So that's the formal framework. Now, let me try to relate it to things you already know. And maybe many of you have already seen the connections. So one thing this reminds you of is interpolation, right? Like interpolating a polynomial from a few examples, and then you can predict it on the remaining points. Another thing this may remind you of is the Fourier transform. That's maybe not the way everybody here thinks about the Fourier transform, but it's maybe an applied math engineering viewpoint of Fourier transform. That Fourier analysis allows you to learn a function f from input-output examples, where the measure on x is a natural measure under which the Fourier transform is defined, and under reasonable assumptions, boundedness, or norms, and so on. But Fourier analysis, if you try to learn, so you can do all of this, okay? Learn a function just in this black box fashion, approximately, interpolate, extrapolate, from Fourier analysis. What's the catch? Why do we need machine learning? And the catch is that this is practically infeasible if x is in is an n-dimensional vector, then you need that cutoff thing is exponential in n, number of samples, and also exponential of n computational time, just to process those samples. These are all rough figures. And the catch is that in practice, n could be like 10 to the power 4, 10,000 or more. And exponential of 10,000 is a gigantic number, way more than the number of elementary particles in the universe. So that's the kind of time or samples you don't have. And in practice, you may have, say, 10n samples. And you have to learn the function from that. So now you're wondering, wait, what is this amazing new Fourier analysis or whatever that has been invented? How can you do such a thing? So instead of Fourier analysis, we use a very naive and trivial algorithm, gradient descent. The algorithm that we sometimes teach in high schools to find roots and so on. So gradient descent is the algorithm where you're trying to improve theta by moving along the negative gradient direction at every step. So you start from some theta, usually random in machine learning, start with a random vector, and now at every step, you improve theta or move theta to minus eta times the gradient. Now, since gradient is the direction of maximal change for a function, minus gradient is the direction where it decreases. And eta is called the learning rate, which has to be set appropriately, say 0.01. And that's what you do. And pictorially, you are in this landscape of the loss function, and you're just following this path of small but steady improvement. Now, as this figure suggests, a complication, a mathematical complication, which we'll return to, is that this loss function is often non-convex, especially in something called deep learning, which we'll see in a minute. And why is that important? Well, as in many other areas of mathematics, convexity goes with niceness. So there's a very nice theory of optimizing convex functions. Non-convex is difficult because, of course, it could have these peaks and valleys, and gradient descent may end up in the wrong place. So we'll return to that question later. I also want to note that in practice, this simple algorithm, gradient descent, is improved with tricks like time-varying learning rate, memory of past gradients. It's kind of counterintuitive, but it helps to have the past gradients. That's called momentum, regularization, etc., which I won't describe today, but are very important. I also want to note that this gradient descent, which seems naive, actually, there's a mystique about it. And it's actually really quite remarkable. People think it's the natural algorithm for learning. It's how people think learning happens in biology, evolution, etc. You follow the natural path. And it does seem that in machine learning, it finds nicer solutions than you would expect. And we'll return to that issue later. And so now, without further ado, is deep learning in a slide. So we've developed the formal framework, and then deep learning is very simple. It's just a model that's a bit more complicated. It's multi-layered. That's what deep refers to. And the model involves applying a sequence of transformations, these different layers, on the input vector, x. And what are these transformations? Very simple. Alternations of a linear transformation and a nonlinearity. And for this talk, linear transformation is just multiplying by a matrix. And nonlinearity is, given a vector, zero out all its negative coordinates. So if you now compose such transformations and you get an output at the end, that entire transformation is piecewise linear because this nonlinearity is piecewise linear. It's a very simple, mathematically, very simple class of models, but it's nonlinear. And the training is exactly as we saw before. Okay, we already saw this framework. But remember, to train, you need the gradients of the loss. And to compute the gradient, you need to contend with this term, f sub theta of x. X, of course, is a constant, right? X is given. That's the input. Theta is unknown. So you have to differentiate respect to theta. And that, if you look at it, this is a composition of functions. So the thing that comes to mind is chain rule. And yes, if I ask you to sit down and think for a little bit, you'd write down an expression for the gradient using chain rule. And there's an algorithm called backpropagation which does that, but does it in a very clever way so that it's more efficient. It rearranges terms in a clever way, and that's very important. By the way, from now on, I'll have these notes at the bottom, which I won't read out. These are like footnotes, and it's only for advanced audiences, in case you, especially if people are watching this on a video later on, if they want to follow up on these in some way. Okay, so, and by the way, as I already indicated, deep learning is the champion in many tasks today. Why does it work? And the best guess is that it's nonlinear enough to express many things, interesting things, and it's linear enough that it can be implemented very fast on today's computers and GPUs. Okay, so with that formalization, that was the longest part of the talk. Let's talk about machine learning in action. And these are going to be less trivial tasks. Okay, but it's the same framework. That's the striking thing. And the key idea is that we'll need to define this loss function for learning in a more creative way. So let's return to this movie rating task where you're predicting the score. And we use a simple linear model. And when you show it to students, they often complain, wait, this is not how we humans do it. For example, word order in text matters, right? And also in mathematics, order matters. No good versus good, no. We don't need millions of examples because we understand language. The very first time you read an Amazon review, the very first Amazon review you read, you knew what the sentiment was. Nobody needed to give you millions of examples to train you what sentiment is. And yes, science has long tried to understand and formalize language plus semantics. If you think about the ancient Greeks with their propositional logic, that's an attempt. There have been more attempts using grammars, Chomsky grammars, model theory, all kinds of things. And indeed, people for many decades did try to write machine learning programs that use that, and it didn't quite work so well. So how can machines understand language? Which arguably is much more general purpose. Once you understand language, you can do all kinds of things, not just rate movie reviews. So this is the domain of unsupervised learning. And the paradigm here is that the model is going to be trained on tons of text that's available online. For example, Wikipedia. So the key idea is to use a large corpus like Wikipedia, okay, so no human supervision, just the corpus, train the model to predict part of the text from the surrounding text. So for this talk, think of it as a little bit more simplistically as predicting the next word. So I went to a cafe and ordered a blank. Now, suitable completions could be coffee, croissant. Puppy would be kind of nonsensical. Of course, this is a task that, for instance, your phone is doing when you're typing in. It predicts the next word. So using the kind of framework that we've already seen, you can train a model to learn to do such completions. And in the process, the model must implicitly pick up on rules of grammar, right, which you need for completion, some common sense, the fact that you don't order a puppy at a cafe, and it starts to understand language in some sense, and we'll see in what sense. And these models are, of course, used in your smartphone, machine translation, etc. Okay, so what's this language model? Well, this model is a little bit different than before, right? It's going to train on a large text corpus. And this model is trained on the following task. Given the last 5 words, W1 through W5, predict the next word. So prediction means it gives you a distribution on all 100,000 English words. Okay, the probability of the next word. So for instance, coffee may have probability 50%, croissant 30%, etc. This may look like a little bit weird, outputting a distribution, but realize that this is something you see every day in the newspaper, right? The weather forecast. And but the difference is that in the weather forecast, the probability distribution is on 3 or 4 things, right? Sunny, rainy, cloudy, etc. And here it's a distribution on 100,000 English words. And the way this deals with that is to not represent the distribution explicitly, but implicitly, in the style of statistical mechanics. So the probability of the next word being W is proportional to, oh, sorry, I forgot to say this. OK, it says there, but I forgot to read it out, that the parameters on in the model is a vector for every word. So remember in the earlier learning ratings model, we had a scalar, sentiment score for every word. Now it's a vector, 300-dimensional vector. 300 is not so important. It's just enough direction so that you can represent semantics. OK, so now back to the description of the distribution. It assumes that the probability of the next word, given the last 5 words, is just the average inner product of the vector of this word with the past 5 words, with the vectors of the past 5 words. In the style of statistical mechanics, this distribution is described using proportionality. Probabilities have to sum to 1, so there's an implicit normalizing term which makes the sum equal to 1, which I'm ignoring for this slide, for simplicity. So how do you train this model? OK, so initially, of course, you don't know the word vectors, and you'll start with some random word vectors. And you want to train it, so you want a measure of goodness of fit. And to understand the goodness of fit, well, let's realize that, how do you even understand goodness of fit for the weather prediction, right? If the prediction is 60% rain, it could either rain or not rain, and both are in some sense correct, but rain is a little bit more correct. And so the loss function we use is, well, it's the reciprocal of probability, but we're interested in the probability that this language model assigns to Wikipedia. Take all of Wikipedia, billions of words. What is the probability that this model assigns to that? In the following sense. So if you factor it out using Bayes' rule, well, given the last 5 words, the probability of WI is some expression. And the probability assigned by the model to this entire sequence in Wikipedia, n is billions, is the product of those terms, which you can express in this using exponential in this nice way. And so the loss is the reciprocal of this probability. So if the model does not give enough probability to Wikipedia, you try to improve it. And how do you improve it? Well, you start with a random theta, random vectors, and then you just minimize this loss, okay, for which you have an analytic expression. So that's the idea of a language model. And what does it give you? So there's all kinds of amazing things it does. And let me give you just a tasting. So in this model, we had a vector for every word. So these are called semantic vectors. And lo and behold, after you train the model, you look at these vectors, and you see that the inner product of the vectors captures very well human notions of similarity. So if you ask humans to rate similarities of pairs of words, lion and tiger are similar, tiger and coffee are different. So you ask them to rate on a 0 to 1 scale the similarity, and those human estimates of similarity are captured by this model pretty well, even though the model had no idea of human similarity notions. So somehow it's capturing things that intuitively goes on in our heads. It's possible, so there's a lot of work on trying to extend this to language models, not just word models. And it's possible, in a paper of ours, we showed that it's possible to use just word vectors and some linear algebra to define a vector that captures the meaning of longer pieces of text, like sentences and paragraphs. And it also has a similarity property, that it captures human notions of similarity. Indeed, if you incorporate movie vectors into your, semantic vectors into your movie rating task, the one earlier, you improve the performance. And finally, a recent discovery shows that actually these word vector spaces for different languages, say English and French, can be meaningfully aligned via linear transformation, so that, say, man ends up on top of And that's caused a lot of excitement. So somehow these models, they're trained in a simplistic way, but they seem to capture a lot of properties of languages. And by the way, this will make an appearance, a guest appearance later on as well, this capturing similarity of sentences or paragraphs. So now you're thinking, OK, and this is what the students say, OK, fine, interesting. You can predict review scores. You can passively understand language meaning by reading a lot of text. But how can machines actively interact with the world via a sequence of intelligent decisions, which is what we think of as intelligence? Now, there's antecedents for this in mathematics and science in the 20th century. So for instance, in probability theory, there's betting games or martingales, etc., which is repeated decisions. Economics, managing stock portfolios, playing repeated games. Control theory for controlling complicated power plants, etc. And what I'm going to describe is descended from that. So this is a sequential decision-making framework in machine learning, which for simplicity, I'll describe using game playing. But it can be used for all kinds of other sequential decision-making. So the framework is that as I said, I'm using game playing. So players alternate with white and black playing their moves. And there's a tree of all possible actions, interactions. And I'll assume for today that the responses can be stochastic. So the opponent may choose probabilistically between possible moves. And now, what is the optimum first move of the white player? Well, remember that at the end of this sequence of moves, right, meaning each of the paths in this tree, either you lose or win. And let's say 1 corresponds to loss, a lost 1, and 0 is a win. So what is your optimum first move? Well, it's the one that minimizes the expected loss over this entire tree, right? You evaluate the tree, and that's your expected loss. Assuming you know how white is playing and how black is playing. So you not just at the first step, but also later on. So if you have a model for how white and black are playing, then you can analyze you can compute the optimum move. Well, I say you can compute, but not really, because this tree is too large, right? It's depth 50 or 100, and there's just ginormous number of nodes in this tree. So it cannot be evaluated completely. And of course, you've all heard about the chess playing software in the 90s, which was already a world champion. And the idea there was that you have a list of handcrafted rules based upon input from chess players and chess theory, which already prune the set of possible moves a lot. And then you prune it further by using a move look-ahead algorithm, which is approximate and does some kind of a Markovian search of the tree to evaluate it. So that's not. So what did the new development about Go involve? And as you may imagine now, we have handcrafted rules. In the framework of machine learning, there was no role for that. So that goes out the window. We're not going to use handcrafted rules. And what are we going to use instead? A model. A parametric model. And we'll still use this algorithm for look-ahead. Actually, even the look-ahead is done with a model, but let's ignore that complication. So this is how it works. This is a crude account of the program that is a Go chess champion. So now the decision maker is a model. Parametric model, it has some parameters, again, millions of parameters. Given a board position represented as a vector, it outputs a distribution on moves. So all this makes sense based on everything we've seen so far. And of course, this model is going to be used throughout the game tree. So given that this model is going to be used throughout the game tree, and maybe there's also a model for the black player, so it can be used throughout the game tree because the number of moves that have happened so far is also an input to the model in the board position. So you can use the same model everywhere in the tree. And now using your Markov tree search exploration algorithm, you can evaluate the moves. Okay, so approximately. So let's say you have an evaluator for the moves. And so you can evaluate this loss function L of theta, okay, for a move. And so you can evaluate it on a distribution of moves, etc. Okay, so maybe there's some details here, but nothing that you couldn't recover within a few minutes of thinking about it. And so now the idea is to estimate, you train this model, again, by estimating the gradient and improving theta. Okay, so gradient descent, you start with a random value for the parameters of this model theta and do gradient descent using this loss function. But now the loss function, unlike the previous settings, is not explicitly given to you, like this exponential or whatever. It's just implicitly given to you by value. You can evaluate it, but you don't even have access to its parametric description. because that's too complicated. So, but a crude method could be, even if you know how to evaluate the loss function, evaluate it at theta and at theta plus eta, where eta is some small Gaussian noise. And for small eta, the linear approximation would be valid. And if you do it for a few random etas, you can recover the gradient. So that's the idea. This is very, very crude. I mean, there's a lot of ingenuity to actually compute the gradient. That's actually one of the most mathematically difficult part of this area. OK, so now I'll talk about mathematical understanding of deep learning, some of my work and other people's. And this has all happened only in the last few years. So we already saw what's deep learning. It's this machine learning using a model where the model has these alternating linear and nonlinear operations. So some key questions. When and how and why does gradient descent work, and how fast? I apologize again for these slides being squished in some way. And as I mentioned, the loss is non-convex, and so it's not clear what it means for this to work. Does it end up in some bad valley, or where? Another question, why deep? Today's models have hundreds, even thousands of layers. And for the longest time, people thought that's crazy. That should not help. But somehow it does help. And so why deep and not shallow? Here's another mathematically very interesting question. Why doesn't training overfit to training data? Now, you may remember from the polynomial interpolation example, if you have a degree d polynomial, you can, given d plus 1 points, you can learn it. But if you have too few points, of course, you can always fit a polynomial. So there is this phenomenon of overfitting. So there was this earlier example of inflation versus unemployment. And here's a different model you could fit, which is more complicated, which tries to fit the data even better. And of course, that's overfitting because it won't predict the new data. So remember, 20% of the data was held out. This will not work. So you'll reject this kind of complicated model, and you'll stick with the linear model. And so today's models have way more parameters than training samples, and nevertheless, they don't overfit. We know that these models have enough parameters. They can even fit random data. Random pixels, random labels, everything random. They fit still pretty well, because they have so many parameters. But when you train it on real data, somehow something magical happens, and it doesn't overfit. It's a scientific mystery today. And finally, how to interpret the trained models' inner workings. This I won't talk about too much today. Won't have time. So analysis of optimization. So the first hurdle is, as I said, non-convex optimization is very difficult, complicated. It's from complexity theory. It's NP hard, so no efficient algorithm if p is not equal to NP. And the second hurdle is that this loss L of theta is essentially a black box to us being mathematics. So now you'll say, wait, black box? You just wrote an expression for the loss. This, right? Everything is known here. The mathematical expression is known. What is a black box? Well, the black box is that we lack any mathematical description of the data, these xi, yi's. Going back to the question I started with, what makes a bunch of pixels an image of a dog? There's no mathematical description of that. And probably deep learning is possibly the only description we'll ever have. So that's a little bit disconcerting for a mathematician, because before you work on an object, you want it to be well defined. And so how do you do any mathematics with it? You work in the black box model, which is quite traditional in optimization theory. And by black box, we mean here that you can evaluate the loss function. Given any theta, you can evaluate it. And you can evaluate the gradients. OK, so those two we know how to do. So that's all we know. So if that's all you know, then the black box analysis goes as follows. So remember, we are following the direction of negative gradient. So long as the gradient is non-zero, it seems like there's a descent direction, right? By definition, from multivariate calculus. By the way, this is a great example. Deep learning is a great example to motivate high schoolers about calculus. Because these days, a lot of the high schoolers I'm seeing have already downloaded deep learning software and are playing with it and everything. OK, so if gradient is non-zero, there's a descent direction. But if the Hessian, the second derivative, is large, well, by definition, the second derivative determines the rate of change of the first. So it allows the gradient to fluctuate a lot. And so since you're making only a finite step, right, not an infinitesimally small step, but a finite step, it could be that when you take that step, the gradient has moved enough that you would end up making no progress. The loss can decrease. But that happens only if this Hessian is large. There are techniques to actually trim the Hessian, make sure that the loss function doesn't have a large Hessian. But also you can do is you can take a small enough step determined by the norms of the gradient and the Hessian, and then you can ensure that you at least end up in a to get close to a point with gradient roughly zero. So that's a stationary point. By the way, Michael Jordan is giving a lecture tomorrow, plenary lecture, which discusses these kinds of optimizations in more detail. By the way, there's a more complicated analysis which shows that you can get not only to a point with gradient roughly zero, but actually also where the Hessian is positive semi-definite, which is like a local minimum, in the bottom of a valley. So that's the best you can do with black box analysis. What about non-black box analysis? So the setting where this has been successful, these are you can think of them as very simple deep nets. And maybe these problems are a little bit more familiar to this audience because you may have seen them as part of applied mathematics, inverse problems, Helsinki problems, etc., where you assume that the data was generated according to some clean mathematical model. And so the optimization landscape for this loss is much more well understood, and the desired optimum is this ground truth model that was generating the data. So some buzzwords, I'll only give you buzzwords. There are things like phase retrieval, matrix completion, topic modeling, sparse coding, tensor decomposition, learning, hidden Markov models. These you can think, you can think of as applied math problems. There are probably even talks in this conference about some of these. And you can think of them as learning special neural nets. And the idea in the analysis is that you prove something like a Lyapunov function, that at every step, the direction of movement in this algorithm is correlated with the global direction. So you're making progress. So this framework is described in a blog post, because it was in some papers, and we just extracted it out for a blog post. So returning to some of the other questions, why deep? Well, the intuition is that even though each layer is simple, a linear operation or this very simple nonlinearity, when you compose these operations, you get something more expressive. And there's evidence from biology. For instance, the human visual cortex has 6 to 8 levels of processing. And some of the lower life forms actually have only 2 or 3 levels. So clearly, more depth seems to buy some expressivity or power in biology. And mathematically also, there's an intuition that, yeah, if you have, say, expressivity for polynomials is like the degree, then if you compose 2 cubic polynomials, you get a degree 9 polynomial, which is more expressive. So there have been some results lately which show that, which transform this intuition into a proof that there are functions, mathematical functions, computable with, say, depth d+1 nets of a certain size, which is not approximable by a depth d net of, say, even size s squared. Okay, so there are results like this. You can think of that as some kind of an approximation theory result. And indeed, the sketch is, as you would expect from that intuition, that it characterizes a maximum number of oscillations computable by a depth d net of a certain size. And you show that there's a gap between d and d+1. OK, so an open question here is exhibit this kind of separation for a natural learning problem. And currently, this is out of reach for mathematics because, as I pointed out, we lack a good mathematical characterization of what a natural learning problem is. So here's another example, another suggestion. Why deep? And this is a new paper of ours with Cohen and Hassan, which suggests that maybe it helps optimization. And I'm running a little short of time, so I'll quickly run through this. And this is just regression, learning linear models. And this is the most classical model in curve fitting, but with an L4 loss. And even here, if you increase the depth and make it non-convex, it actually improves optimization. So you replace theta by a scalar times a vector, beta times theta, which turns out you can think of it as a network with depth 2. So you look at it and you say, wait, scalar times a vector is the same as a vector. So you haven't changed the problem at all. So is it unchanged? No, you have changed the optimization. So you haven't changed the problem. You're still fitting the same model, but you've changed the optimization, namely the path followed by gradient descent. And the path looks kind of different from gradient descent, and turns out it has an adaptive learning rate, time-varying learning rate, and memory of past gradients. And this is what's called acceleration. And indeed, empirically, it accelerates even classic regression, something people have known for decades, if not hundreds of years. Okay, so increasing depth even for regression can speed it up. Why no overfitting? So you can train a model with 20 million parameters on 50,000 examples. We've done it, it works. And there's a popular conjecture that when you're training on realistic data, somehow the net's parameters are constrained either by the problem or the training to be highly interdependent. For instance, people often use the term some manifold of lower dimension. So the next few slides will show you some recent work that is a partial realization of this suggestion. And the mode of this work is that we look at a few trained nets. So this is ICM2018 that was a very successful model for recognizing images a few years ago. And we go and examine it carefully, the trained model. And we find, OK, the properly trained nets that we're examining have some noise stability property. We've done it with several nets, and we find this. And then we prove a theorem showing that this implies that their parameters lie in a lower dimensional subspace. By the way, this dimension reduction idea also appears in Asaf Naor's plenary lecture tomorrow, in a very different setting. So here's what I mean by noise stability. So this is the experiment. So you take a trained net, so it has multiple layers, and you do the following experiment. You inject, so each layer is producing some output, which is a vector. You're going to add a random noise to that vector, a Gaussian vector. So you add a Gaussian vector to the output of a layer. How much Gaussian? The norm of the Gaussian noise is equal to the norm of the vector that was being produced there. It's a lot of noise. So now you would imagine everything goes haywire. You're injecting all this noise, the network will output garbage. Well, that doesn't happen. So here's a plot which shows you inject noise at various layers, first layer, second layer, et cetera. The different curves show you that. You inject the noise, and you see how much noise appears in the subsequent layers. How much do they deviate? And initially, you start with noise ratio 1, as much noise as the vector that was there, and it quickly drops to 10% or so, 15%. So the network, the trained network, rejects the noise that you inject, which in some sense is kind of like what learning is, right? It sort of rejects irrelevant things. Now, this may remind you of noise-tolerant circuits, which von Neumann had to invent because, of course, he was creating computers and circuits using vacuum tubes, which failed. And the main idea was to improve reliability of circuits by allowing redundancy. So indeed, that's the idea, that these trained nets have a lot of redundancy, and you can exploit that redundancy to put them on a lower dimensional surface. So here's a very quick explanation using just a linear layer. Okay, the theory applies to nonlinear, but I'm explaining it using a linear layer. So this layer has a matrix M, and if you input x, it gives you M times x. But if you input x plus noise, eta, you get M of x plus eta. So since if the layer rejects noise, that means that the ratio of mx to x in norm must be much more than the corresponding ratio for noise. Now these quantities can be understood. The left-hand side is, of course, the largest singular value. And the right-hand side, well, Gaussian noise distributes itself evenly in all directions, so in all singular directions. So it turns out it's related to the L2 norm of the singular values. So this inequality is showing that the largest singular value is much more than some average, L2 average. And indeed, empirically, if you look at, say, the layer 10 of VGG19, you find that there are a few large singular values, and then the rest drop off. They drop off, but they're not zero. Okay? So it's not like the matrix is low rank, but just effectively low rank. So this is called the layer quotient. So now the proof is that this noise stability implies that the deep net can be made low dimensional with minimal change to training error. So the idea is that you can do a compression, and the compression is this random linear projection. You take random matrices M1 through Mk, and K is pretty small, and these are picked randomly before you see the data. Okay, so you have done it in advance, and you project the matrix linearly in the space of these matrices. You treat them as vectors, and that way you think of it as a linear subspace. And this compression, you can show it, the errors that it introduced are Gaussian-like. And therefore, as it percolates through the network, they get attenuated, so the output doesn't shift too much. So this K is logarithmic in original size, so the matrix becomes low-dimensional. And by the way, Gil Kalai's talk tomorrow, plenary talk, is also about noise stability, but in a very different setting. But this idea of noise-stable circuits appears there. So, which brings me to the last part, taking stock and wrapping up. So when we teach this kind of things to new audiences, the reaction is, wait, this is mindless model fitting, right? The mystique is all lifted. And none of this is remotely how humans think. And maybe that's true. But here are some answers that I give. The imitation approach has not worked so well in the past. When we tried to design flying machines, we didn't try to imitate the nature's flying machines which flap their wings. So we tried to utilize things like jet engines and other things that machines have and nature doesn't provide. And in this case, the machine's advantage lies precisely in the ability to crunch data. It can crunch millions or even trillions of bits of information, which humans just cannot. And indeed, I think that machine intelligence, if you can call it that, will probably develop in a very different way than human intelligence. On some tasks, it'll get better and better than humans, and others, it may take a long time. And finally, the most difficult, and the most difficult issue is that we have very little idea at an operational level how humans think. Okay? We've used intuition about what's going on in here for thousands of years, and we really still don't know. And in fact, machine learning, I mean, it's the opposite. I don't think you'll improve machine learning by using something about humans, but in fact, you'll use machine learning to understand what humans are doing. And here's an example of something I was involved in. There are many people trying to apply machine learning to neuroscience. And this is a paper that I did with neuroscience colleagues at Princeton. So this is about fMRI experiments. So what's the experiment? You have a human subject fully awake. Right? There are very few techniques that look inside a brain when you're fully awake. So fully awake, lying in the scanner, and it measures the amount of blood flow, local blood flow, at 50,000 points in your brain. Okay? It's kind of like a fluid measurement system, right? Like measuring the flow in a river. So it does that. And in this case, in this experiment, the subject was watching the Sherlock Holmes movie. So he watched it for 20 minutes, and then you get this voxel vector, 50,000 dimensional vector, describing blood flow at each time step, every couple seconds. And now the task is that they want to understand how this blood flow corresponds to the stimulus being presented, the movie they're watching, which when I first saw it seemed crazy. Like, this is not a fluid mechanics problem, blood flow. But, you know, blood flow correlates with mental activity, so it sort of makes some sense that there's some signal there. So how do you capture that signal? And the difficulty here is that the signal is a movie scene, which has moving images, lots of pixels, sound, explosions. It's a complicated signal. And you wanted some simple representation of the signal, which preserves some of the semantics. So the idea my colleagues had was to use a text annotation for every time step of the signal. So annotations like, in this scene, Sherlock and John are talking about the murder in an old room with Mrs. Hudson, etc. So for every time step, you have this annotation. And now decoding would be, the ultimate decoding would be, looking at the fMRI, you can tell what the signal is, what the semantics was, and looking at the semantics, what the fMRI was. That would be the ultimate decoding. I don't think that'll ever happen. But there's a weak form of decoding that people do that, let's say you have signals from 5 time steps, the fMRI readings and these annotations. And you randomly permute them and ask the machine learning program to say which time step corresponds to which time step. Okay, match up the signals again. So you permute the annotations and the fMRI, 5 of them, and then have to match. So that's a very weak kind of decoding, if you call it. That's what they call decoding. And so how do you decode? And notice that this is not your typical applied math problem, for instance, X-ray tomography or other things, because there's no mathematical model for language, right? So now you see where this is going. As I told you to bookmark mentally, there was these notions of capturing the meaning of text via vector, semantic embeddings. And so we replace the annotations with those semantic embeddings, and then we learn a linear transformation between these two spaces, which aligns. And yeah, you can do the matching task with something like 80% success rate. Okay, so indeed, this is the hottest trend in academia. Apply machine learning to discipline X, where X could be all these interesting disciplines. And I'm hoping that this amazing audience will also pitch in and join in this development in understanding machine learning. And so concluding thoughts, I started with these simple, naive questions, but clearly philosophically important. And I hope I've given you some idea of how we are approaching these. And machine learning speaks to age-old wonders and mysteries. It's a new way of looking at the world. We are complicated and inexact descriptions. We don't have a simple Newton's law here. We have complicated, inexact descriptions which we embrace. And it's a new frontier for science and math in all kinds of ways. And I'm optimistic that deep learning methods can be mathematically understood or simplified. Thank you very much, and I'll end with this familiar. Could I say one more thing? Yeah, I forgot to put it on the slide, but next year at the Institute for Advanced Study, where I am for the next few years, we have a special program devoted to machine learning. So in the math department, devoted to machine learning, statistics, and optimization. If some of you are interested, please let me know, send me email. It's 2019-20.
Thank you for such an inspiring lecture. And as all of you may know now, it's not possible to ask directly questions to Professor Arora, but of course, please do in private. And let's thanks again, Professor Arora.